Okay. All right, let me share my screen. How was it? What were your thoughts? I felt like you guys did pretty well when I was looking through through your answers. How did you guys think it was?
I thought it was all right.
I feel like buffers were like just the one thing that really like you guys weren't quite there on, but I feel like a lot of the other stuff you've done really well on. Like I feel like the salts and the buffers were the difficult things, but that's also the newest material, so it makes sense. But a lot of the other stuff you guys did really great on. I thought you guys didn't do great on that too. Just felt like it was the weakest point. Any other thoughts? You can unmute or you can type in the chat. Okay, so if not, then we can just get started going over the exam. So for the first question here, it was to identify the Bronsted-Lowry acid, the Bronsted-Lowry base, and the conjugate acid and the conjugate base. And then when I looked through, it seems like you guys had done really well in this one. So does anyone want to start off by saying which one was the conjugate, or sorry, which one was the Bronsted-Lowry acid or the base?
The first one was the base, and then the second one was the acid.
Yes.
The bronze low.
So we have, the C, just like Lone said, the CH3 NH2 is the base, because if you remember the Bronsted-Lowry definition, it's like the acid is the proton donor and the base is the proton acceptor. And so as you can kind of see throughout the reaction here, the CH3 NH2 ends up actually gaining another proton to become CH3 NH3 plus. So it means that it's gaining a proton, it's a base. So CH3 NH2 is the Bronsted-Lowry base, and the water in this case acts as the acid because it's the proton donor. And then kind of on the flip side of that, if you remember, the Bronsted-Lowry base then becomes a conjugate acid because now it's gained a proton that it can lose. And so in this case, the CH3 NH3 plus is the conjugate acid, and the OH minus is the conjugate base of water. Are there any questions at all about that one? Okay. Then if not, we can go to the next one. So the next one was ranking acid strength. And so there are 4 different molecules, H2TE, HI, H2S, and NHS or NaH. Were there any that you were immediately like, this is either the strongest or the weakest out of all of them?
The HI is the strongest, right?
Yeah, exactly. Because the HI is the strong acid. So you know that HI has to be the strongest one here. And then were you able to figure out which one was going to be the weakest of the acids?
The NaH.
Exactly, because if you remember, like in order to actually be an acid, the proton has to get donated and like have that positive charge. But in some of these compounds like LiH or NaH, like you end up having the proton taking on more of, you end up having the cation, the Na and stuff taking on the more positive charge, because because it wants to be it only needs to lose one electron to become stable. And so sometimes the Na or lithium, if they're in that first row, or for the first group of like alkali earth metals, I think it is, when they're bonded to H, they don't really let H be an acid because they're not gonna let the H take on that positive charge and be an acid. So yeah, just like Bryce said, NaH is definitely the lowest or like the weakest acid, and I think it was Kelly who had said that HI was definitely the strongest acid. And then when we have to go from there to figure out between H2S and H2TE, which is the weakest out of the two of them. So do you guys remember the trends with binary acids? There are 2 like main trends here that are important to consider. Do you remember either of them?
Size, zone.
Yeah, exactly. And so for one of them, I just Google periodic table. So there you have the one where you have size increasing as you go down a group. And so, for example, here, if you have go down a group, you're going to get larger because you're adding an electron shell on there. And then that bond between the proton, the H, and the anion is going to get weaker as the atom gets larger and larger, because the bond is weaker between a larger atom and a smaller ion, or a smaller atom, than it is between two smaller ones. And so because of that, the larger it is, the stronger the acid, because the weaker the bond, the easier the H can leave. What's the other trend that you have to consider for binary acids?
Isn't it electronegativity?
Exactly. So as electronegativity increases across the period, acid strength increases because the bond gets more polarized, and that electronegative element can take on the negative charge once the proton leaves more easily than a less electronegative element. And so in this case, the two things we're comparing H2S and H2TE. And so we have H2S here and H2TE here. Because they're in the same group, which trend do we have to consider? Electronegativity or size?
Size?
Exactly. And so which one will be the stronger, H2TE or H2S?
H2TE. Sorry.
Exactly. Yeah, exactly. So the actual ranking of them is NaH, H2S, H2TE, HI. Are there any questions at all about that? Or like acid strength at all? Okay, great. Okay, so for this next one, we have which is a stronger base, PO43 negative or ClO43 negative. This one I think must have been confusing to a lot of people, because I think that a lot of people chose the wrong answer. So at least I didn't see. I think most people knew that they're going to be different in strengths, which is good, because since phosphate and choline are in different positions on the periodic table, you'd have they wouldn't have the same strength, because you have that difference in electronegativity and in size. And so this one's kind of strange, because PO43 negative is actually a stronger base, because the conjugate acid is weaker than the conjugate acid of ClO43 negative. And so let me pull the periodic table here. So it's kind of like the opposite trend when you consider, because Cl is going to make a stronger acid because it has a greater electronegativity. It's kind of the opposite for the base, where the base, like this PO43 negative, wants to have a proton more strongly, because it's less stable than the ClO43 negative would be, because they're kind of because if you think of them both as conjugate bases, you have H3PO4 or you have H3 ClO4, and so, or HClO4, and just would still be negative, because you have the only difference being here in terms of electronegativity, because they both have the same number of oxygens, and they're both in the same period. Because of that, since the Cl has the greater electronegativity, it can hold onto the negative charge more easily once the proton leaves. And so because the phosphorus, the phosphate ion here, cannot hold onto the negative charge as easily, it wants that proton more, because it wants to be able to be more stable. And so the PO43 negative is actually the stronger acid, or sorry, the stronger base. Are there any questions about that? I know it's kind of confusing to think about, because it's kind of like the opposite of your acids.
Yeah, wait, I'm still kind of confused. You mind explaining that again?
Of course. So one way to think about it is that the conjugate acid of PO43 negative is weaker than the conjugate acid of ClO43 negative. So if you remember, you have HClO4 is one of the strong acids, and then you have I think it's H3PO4 is phosphoric acid. And so we know that HClO4 is one of our strong acids. So HCl4 is a really strong acid, but phosphoric acid isn't as strong here. And so you have it kind of be the opposite, where the conjugate acid or the conjugate base of a weaker acid is stronger than the conjugate base of a strong acid. And that should kind of make sense when you think about how like strong acids dissolve in a solution, and when they dissolve in like water, you have the ions be like completely separate. But you have for a weaker acid, you have them wanting to glob back onto that proton because they're not as stable without the proton as they were before. So like the ClO4 negative can survive really can exist really easily, really stably without a proton, because Cl is really negative, electronegative. You have oxygen's bonded to it too, so you have a lot of resonance structures, you have a lot of stability there, that formal charge can be passed around, the negative charge can be passed around, but the PO4 negative isn't as electronegative as the ClO4. And so it can hold onto that negative charge, but not as stably, not as easily as the ClO4. And so it really wants a proton. It wants to gain a proton so that it can be more stable. And because of that, it's the stronger base because the conjugate acid is weaker. Does that make sense?
Yeah, a little bit. Thank you.
Yeah. How are there? Does anyone else have any questions, or does that make sense to the rest of you guys?
No, that makes sense.
Okay. Okay, so I really misspelled because okay, so then we have this next one here. The three diagrams represent three different solutions of the binary acid HA. Water molecules have been omitted, so you just see the acid and you have the hydroniums. And the hydroniums are just represented by H+. You don't have to like worry about like you have like the H+ are the purple ones, but then the acid, the HA is the purple and white, and then just the A is the white here. So when you see like the HA, that's them bonded together. When you see them separated, that means that they're like completely dissociated. And so what do we know about dissociation and acid strength? Does a acid dissociate more or less if it's strong?
More.
Right, like a really strong acid, like HCl will just like completely dissociate. The Cl's completely break up from the H's. And so in this case, you have the stronger acids are the ones that have dissociated more than the weaker acids. And that should make sense because if you remember, the whole point of an acid is that it's a proton donor. And so if it's giving up a proton, it should be really easy for the two of them to separate so that that proton can be like donated to another ion from the HCl. And so, or for example, the HCl from the strong acid. So in this case, the A would be the strongest acid because it's completely dissociated. B would be the second strongest because you have some of these, like these purple white ones are the HA. You have some of them present, which means that like it dissociated most of the way, but not all of the way. And then you have the last one, C, is really a weak acid because you have so many of these HAs. You only have like one that actually dissociated. So it's a really weak acid. And so the order is ABC, with A being the strongest acid and C being the weakest acid. Are there any questions about that? Okay. Go back to the exam. Okay, then we have calculate H3O plus in an aqueous solution that had OH negative equals 1.1 times 10 to the negative 9th molarity at 25 degrees Celsius, and then classify the solution as acidic or basic. So first, does anyone remember the equation that we use for calculating when we have like how to convert between OH concentration and H3O plus concentration?
Would it be that when you multiply both concentrations, it equals 1 times 10 to the negative 14?
Exactly, that's exactly it. So yeah, you have Kw is what Lone just said, that 1 times 10 to the negative 14th. And so you have Kw equals H3O plus times the concentration of OH minus. And so you can rearrange it so that you can just divide Kw by the concentration of OH minus in order to get the concentration of H3O plus positive. And so when you do that, you get a concentration of 1 times 10 to the negative fifth for the concentration of H3O plus. And the last part of it is classifying the solution as acidic or basic. So there's two ways you could do this. One way you could do it is you could calculate the negative, you could do negative log of the concentration, then see if it was greater or less than 7. But does anyone know how to look at this concentration and determine if it would be, if the solution would be acidic or basic without calculating pH?
Well, I remember that if you have more of something, then that means that it's that. So kind of like H3O plus, we have to the negative 5, which is bigger than to the negative 9, which means that it's more acidic, I think.
Exactly. Yeah, that's perfect. Yes, so you could definitely just calculate pH if you just wanted to do it like that. But if you don't want to calculate pH or you were like in a time crunch, you could do exactly what Lone said. So you have OH minus here is 1.1 times 10 to the negative 9 molarity, whereas the H3O plus is 1.0 times 10 to the negative 5th molarity, which means that there's way more H3O plus than there is OH minus. And if you only had the concentration of like just OH minus or just H3O plus, another good trick to know is that if a solution is completely neutral, both OH and hydronium, they would both have a concentration of 1 times 10 to the negative 7th. Because 1 times 10 to the negative 7th times 1 times 10 to the negative 7th equals 1 times 10 to the negative 14th, which is the Kw of water. And so if you have whichever one you have a greater concentration of than 1 times 10 to the negative 7th, it means that it's like there's more of that ion. So it's either acidic or basic. So like in this case, because you have 1 times 10 to the negative 5th, that's greater than 1 times 10 to the negative 7th, which means that it's acidic. I hope that makes sense. Does anyone have any questions about this problem at all? Or anything else I just said?
No, it makes sense.
Okay, awesome. So now for this next one, we had to complete the table. So this is kind of like it was just like this last question, except having to do way more calculations for it and actually solving for pH for it. And so for this first one here, we can just do exactly what Lone had to do for the first one to solve for H3O plus from OH minus. We can like do the exact opposite of that by solving for to solve for OH minus from H3O plus. And so for this one, we start off by using this expression that Kw equals H3O plus times OH minus. Instead of having H3O plus over here and OH minus here, you would flip the two of them. So you'd have OH minus here. So you would divide 1 times 10 to the negative 14th by 3.5 times 10 to the negative 3rd, and you would get a concentration of 2.9 times 10 to the negative 12. Then if you remember pH, to solve for pH, pH is negative log of the concentration of H3O plus. So you would do negative log of 3.5 times 10 to the negative 3rd, and you would get 2.5. And because the pH is less than 7, it's acidic, or you could do what like Lone had talked about, where you look at the concentrations of H3O plus compared to OH minus. Clearly there's way more, because only negative 3rd, there's way more H3O minus or H3O plus than there is OH minus, which also makes it acidic. For the other one, if you remember the equation for pH is pH equals negative log of your hydronium concentration, your H3O plus. So to undo that, to get your H3O plus concentration, you have to do 10 to the negative pH. And so in order to get your H3O plus concentration, you would do 10 to the negative 7.15, and you would get 7.1 times 10 to the negative 8th molarity for H3O plus. Your OH minus, you would just do what we had talked about before, where you would do 1 times 10 to the negative 4th 14th divided by your H3O plus concentration, you get 1.4 times 10 to the negative 7th. And then because your pH is above 7, even though it's just barely above 7, and because you have slightly more OH minus than you do H3O plus, the solution is basic. Are there any questions about that one at all? If you got this one wrong, but you had one of the right answers, it might have just been like a sig fig thing. I had seen that with somebody else's where like you had included an extra sig fig or something. So it might just not have, Canvas might not have registered as correct, but if, as long as your answers match the answer key, I'm sure you did the calculation correct. Are there any questions about that one at all? Okay, so if not, we'll go to this one, which is kind of like a Le Chatelier's principle question. It's the value of Kw increases with increasing temperature. Is the autoionization of water endothermic or exothermic? So the autoionization of water is when you have, if you don't remember, it's when you have H2O and you have two of them, and you end up having them go to H3O plus. Plus OH minus. And so this one, and if it's important to include, this is liquid, and then these are both aqueous. Okay, and so when we write our Kw expression, just like we've done before when we solve for our problems, and like how we talked about Kw being the concentration of OH minus times the concentration of H3O plus. This is where it comes from because your OH or your H2O was a liquid, but your H3O plus and your OH minus are they're both aqueous, and so they'd be included in your K expression. So Kw is just a special case of K. If you remember like your equilibrium K, Kw is just a special case of K. It's just your K for water. And so you'd have Kw equals H3O plus OH minus. Okay. And so that's the equation that you guys have been using to calculate your concentrations of H3O plus or OH minus. So hopefully if you didn't realize this is where it came from, hopefully this makes a little bit more sense as far as that right now. But we have to consider if it's endothermic or exothermic. We have to consider why the Kw is increasing as temperature increases. So if temperature is increasing, how would that, like, if the temperature was increasing and the expression was endothermic, which way would the reaction shift? Would it shift towards your reactants or to your products? If the equation is, if the reaction is endothermic, would it shift towards the reactants or towards the products if you increase the temperature?
Product.
So if you, because endothermic you kind of treat it as adding heat to your reactants. And so if you added a reactant, you would shift more towards your products. But if you were exothermic, so you were adding heat on this side. So if you were exothermic, you'd be adding heat to your product side. If you increase the temperature, you'd be adding a product, which way would that turn your reaction? To the reactants or towards the products? If you were adding heat to an exothermic reaction, would it shift it towards the products or towards the reactants?
The reactants.
Exactly. So if we're increasing Kw as temperature increases, would we want the reaction to be exothermic and pushing the reaction to the left, or we want it to be endothermic and pushing the reactants to the right towards the products? If Kw is increasing, temperature increasing. if KW is increasing, how do we want these concentrations of H3O plus and OH minus to change?
Don't they increase as well?
Yeah, we want them to increase, right? And so which would we want to do? We want to have it be endothermic so that it was pushing towards the product so that the concentrations of H3O plus and OH minus would increase, or we want it to be exothermic and have it pushing towards water and have the concentration of water increase.
Endothermic.
Exactly. So the correct answer here would be endothermic. Does that make sense? I know it's kind of confusing.
Yes.
How are the rest of you guys feeling? Does that make sense?
Yeah, that makes sense.
Okay. Okay, awesome. All right, so next we have determine the pH of a solution that is 1.09% HCl by mass, and it gives you a density of the solution as 1.01 grams per milliliter of the solution. Let's shift it up here. Okay, and so in order to calculate this, that we'd have to do, we'd have 1.09, but to convert it, to figure out what the concentration is going to be of HCl in molarity, because we want to figure out the concentration of H3O plus in molarity, and HCl is a strong acid, so we just kind of need the concentration of HCl in order to determine the concentration of H3O plus. And so we have, because we have a percentage here, we can just like assume that it's going to be 1.9 grams of HCl per 100 grams of the solution, because you just need to keep that ratio of HCl to the solution. So you could have said it would be like 0.109 per 10 grams, or you could have said 109 times 10 over 10,000. We have to keep that ratio. So I think it's easiest to just do 1.09 over 100, because like a whole, you'd be dividing by, you'd be multiplying by 100% to get a percentage. And so this way it's just clear if you have 1.09 grams of HCl over 100 grams of the solution. So the first thing we can do is we can use the density of the solution in order to determine what the did that into liters, and then convert into moles of HCl by using the molar mass. So when we have the 1.09 grams of HCl over 100 grams of solution, we got that because we have the solution is 1.09% HCl by mass. So we're just like, okay, if it's 1.09% by mass, we need to keep that ratio. So we're going to put 1.09 grams of HCl over 100 grams of the solution. Then we have to convert the solution into liters in order to get it into molarity. So we have the density of the solution. So we have 1.01 grams of solution over 1 milliliter of solution. We can convert then from milliliters into liters just using our unit conversion. So it's 10 to the third milliliters in every 1 liter, 1,000 milliliters in every liter. And then finally, you have to divide by the molar mass of HCl in order to get the grams of HCl into moles of HCl. So at this point, you'd have your grams of HCl would cancel, your grams of your solution would cancel, your milliliters of your solution would cancel, and all you'd be left with is moles of HCl over liters, which is molarity. So you should get a molarity of 0.302 molar HCl. And then this all got shifted up weird. But you have, because it's a strong acid, HCl is a strong acid, you just have to do the negative log of the concentration of, this is down here. I'm not sure why it's like this. Sorry. So in order to solve for the pH, is to do negative log of 0.302, and negative log of 0.302 is 0.52. Is the pH of HCl. So the correct answer for number E is 0.52. I'll fix that in the answer key before I upload it. I'm not sure why it's like this. Are there any questions about that one? If not, then we can go forward. So it would be 0.52. I'll fix it in the answer key for why that's not showing there. Determine the pH of a solution that is 0.045 molar in HClO4 and 0.48 molar in HCl. For this one, because they're both strong acids, they're both going to dissociate completely. And so you would just have, and they're going to be, because they're a solution together already, they already have the same volume. So you can just add up the molarities, just like adding moles over liters. And so you just add up the molarities and you would get a solution that's 0.039, or sorry, 0.093 molar. And because they're both strong acids, they're going to dissociate completely. And so because of that, you can just do H3O plus equals 0.093 molar, and then take the negative log of it in order to get the pH. So you would do pH equals negative log of 0.093 molar, and you would get a pH of 1.03. The correct answer for this one was 1.03. Are there any questions about that one?
I have a question. How did you know that you have to add them both? Because I was like doing the balancing equation and I was like, I wasn't sure if to add it or not.
So your pH is going to be your total amount of your H3O plus in your solution, right? And so if you have a strong acid, it's going to dissociate completely. So the H, in this case, the H is going to completely separate from the ClO4, and the H is going to completely separate from the Cl. And so in this case, what you're really doing when I'm saying add 0.045 molar HCl4 and 0.048 molar HCl is I'm really saying like add 0.045 molar H3O plus 0.048 molar H3O plus. That's coming from, this one's coming from the HClO4, and this one's coming from the HCl. And so you're just getting the total amount of HCl or H3O plus in the entire solution after both of these acids completely dissociate. Does that make more sense?
Yes.
Okay, awesome. So that one's just 1.03. But that only works for strong acids. If it's a weak acids, you have to do like the equilibrium in order to figure out how much H3O plus is going to be present. But because they're strong acids, they'll just dissociate completely. For this next one, we have what mass of HClO4 must be present in 0.5 liters of solution in order to obtain a solution with a pH of 1.5. So this is kind of working backwards from, like, we kind of had the opposite here where we already had the mass, or at least the percent mass for that equation, for that question. And here we're kind of working backwards where we're trying to figure out how much mass we need in order to get a certain pH. And so when we do in order to figure out how much H3O plus we need to do, we need to use the equation H3O plus equals 10 to the negative pH, which is just kind of like the opposite, like the inverse of this equation. And so if you do 10 to the negative pH, you'll get the concentration of H3O plus. And in this case, you get 0.0316 molar. Since this is a strong acid, it completely dissociates. So you can just have whatever the concentration is of H3O plus, it's the concentration of HClO4. And so you just use, you already told what the volume is, 0.5 liters, and you have 0.0316 moles per liter. So in order to just get the moles of HClO4, you can multiply the two of them together to get the volume to cancel. And so when you multiply 0.0316 by 0.5, you would get 0.0158 moles of HClO4. And then you can just finally use the molar mass of HClO4 in order to get the number of grams of HClO4 that you need in order to make a solution with this mass. Are there any questions about that? If not, then we'll go forward. This one's was kind of different because Dr. Otinez had talked about how people like weren't like some people during recitation, I guess, or during lecture, you guys have talked about like when you can use a small x approximation, and how people were like, would just look at numbers and be like, I don't even, I'm not even going to waste time doing a small x approximation because I know I'm going to have to do the quadratic on it, or they would just not even test for the whether or not the small x was actually valid. And so she had said that like she wanted to make sure that in study groups we were really testing to make sure that people were actually trying to figure out whether or not small x approximation was valid. And she was like, definitely I'm going to ask them whether or not the small x approximation is valid for things. So I found this question in the textbook, and I thought that it was a good one to go through to see how to do the calculations in order to figure out whether or not a small x approximation is valid. So before we begin, oh my gosh, is this where it went? This is like where it went from above. I'll just delete this. Okay. So do you guys remember what the percentage is when you do the percentage to figure out whether or not the small x approximation is valid? What is the number under which it can be, under which the small x approximation is okay to use?
It has to be less than 5, like same or like less than 5%.
Exactly. And so if you remember, for any acid, because you would have a weak acid, that would go, you'd have a weak acid and it would go from HA to A minus, or should I say H2O plus? But your H2O is liquid, so it doesn't get included in your K expression. So you have liquid, and then you'd have your HA is aqueous. You have A minus, which is aqueous, plus, in this case is, well, I should say in this case, it's H3O plus. Okay. In this case, you are working with HF, but this is the dissociation equation for any weak acid. And so you'd have your water plus your weak acid, and you'd end up having it dissociate. So you'd have your conjugate base, your A minus, and you'd have your hydronium, your H3O plus, which is when water picks up an extra proton. And so when you make your K expression for this, your equilibrium expression for this, you would have to do your reactants over your products. Actually, I already have it written down here. You'd have to do your products first over your reactants, and because you have HA is the only aqueous reactant, only HA would be in the denominator. And so when you end up doing an ice table for these kinds of calculations, if you have your initial and you have your change, and then you have equilibrium, what ends up happening here is that you have a certain concentration, I'm just going to say 1, and you have 0 of these guys, of your A minus and your H3O plus. Or I can actually put HA here. So your concentration of HA is HA, but you have 0 of A minus and of H3O plus. And then what happens is that a certain amount of your HA gets used up, so it's being subtracted from here, and then it gets added to both here and here, because and the value is the same for all of these because your HA is being converted into A minus and H3O plus. And so because of that, you end up having HA minus as your concentration for HA. You end up having X for your concentration of H0 plus and your concentration of A minus. And so when you're doing the small x approximation, you're saying that because the concentration of A is, or HA is so large and your X is so small, that it's basically a negligible amount that you're subtracting by the time that you consider sig figs. And so when you do the small k approximation, you end up just using HA instead of the concentration of HA, instead of doing HA minus X, so you don't have to do Pythagorean theorem. And then you have X squared up top as your numerator because you have your A minus times your H3O plus. So that's where like this whole thing is coming from. So when you do your small k approximation, you do the equations here. Now we actually have a value for Ka, and we have actual values for our concentration of our, here I have it written as HA, but it's HF. And so let me clear. And so in this case, you'd end up having your Ka over your concentration, or sorry, your Ka equals x squared over your concentration of your HF, in this case 0.250 for case A. And you get an x value. Well, first, in order to solve for x, you would do 6.8 times 10 to the -4, which is your Ka value, times 0.25, which is your concentration, and you would get an x value, or you would x squared equals that value, and then you do a square root, and then you get your x value. So here your x value is 0.013. In order to solve for whether or not that was a valid small x approximation, you would do 0.013 molar divided by 0.25 molar times 100%. And you actually get 5.2% here. So if you remember what Lone had said earlier about you having to have like 5% or less, because it's 5.2%, it's not less than 5%. And so the small k approximation cannot be used. So I'll do this again for cases B and C, but are there any questions about any of this? Okay. So let me do it again for B here. And so for B, we have a much smaller concentration. We have 0.05. And so you can be pretty sure that if this doesn't work for like a larger concentration, it's not going to work for a smaller concentration. Because the whole point of it is like if you subtract x from the concentration, it has to be such a small value for x that it's actually like the sig figs don't even matter, because, or the sig figs end up making it so it doesn't even matter that you subtracted a value from it because it's so small. So, but we can just try it out just to make sure of that before you have to make an answer choice. And so you do the same thing that you've done for this one. You do the exact same things. You have a smaller concentration. You have 0.05. So you do 6.8 times to the -10 times 10 to the -4 times 0.05. And then you would square root it because your x is squared. And you would get an x concentration of 0.0058. When you do 0.0058 molar over 0.0500 molar, and you multiply by 100%, you end up getting 12%. 12% is clearly greater than 5%, and so you cannot use your small x approximation. It's not valid here. And then finally, for part C, you have a concentration of 0.025 molar, which is even smaller than the last one. And so you do, again, you would do 6.8 times 10 to the -4 times 0.025, and you would square root it, and you would end up getting x equals 0.0041 molar. You would then do 0.0041 molar over 0.025 molar, and you would get 16, or multiply by 100%, and you would get 16%. So for all of these, the small k approximation is not valid. You can't use it for any of these. Is everyone okay with this? Are there any questions? You can always feel free to type in the chat too if you have any questions, or like private message if you have any questions too, but you don't want to ask them to everybody out loud. Okay. So then for the next one, so for this one, it would have been, you would have to check all 3 boxes to get it completely correct. For the next one, you need to do find the percent ionization of a 0.1 molar solution of weak monoprotic acid with a Ka value of 1.5 times 10 to the -5. And so for this one, you would do the really similar thing to what we just did up here with all of these equations. So you'd start off with the same equation here. You have a weak acid that's dissociating into H3O plus and A minus. And because water is the only other reactant, it all goes over HA, which is your weak acid. And so what you, when you have your setup here, you'd end up having 1.0 times the -5 over HA, which in this case is 0.0 or 0.100 molar minus X, and you have X times X because the concentration of H3O plus and A minus are the same. But here we're going to try it out with the small k approximation, and then we'll go back and check that it's valid. And so you end up having, you solve for your x by multiplying 0.1 by 1 times 10 to the negative fifth. So when you do 0.1 times 10 to the negative fifth, when you do 0.1 times 1 times 10 to the negative fifth, you get 1 times 10 to the negative sixth, and you have it equal to x squared. So when you square root both sides, you get x equals 1 times 10 to the negative third molar. And so for the percent ionization of this, you have to do your H3O plus concentration at equilibrium over your HA initial. And so when you do this, you would do H3O plus is equal to 1 times 10 to the negative 3 molar over your HA initial, which in this case is 0.1 molar times 100%. When you do that, you get 1.0% ionization, which also reaffirms the small x approximation was okay here because it's less than 5%. And so in this case, you would have 1%. Are there any questions about that one?
On the exam, it says that the right answer. Oh wait, never mind. Sorry, I thought it was 0.1.
Did it have the wrong answer on the exam as the answer key?
No, you have the right answer. I'm just not sure where I made the mistake. Sorry.
No, you're totally good. Do you want to do the calculation again real quick, and then I can
Yes,
also do it too to
please.
make sure that I didn't mess it up. So let me go through it. Okay, so we did. You'd have H3O plus times A minus. So you don't have x squared over 0.1, and then you have your k value is 1 times 10 to the negative fifth. So in order to get x, you would do 1 e negative fifth times 0.1, and I got 1 times 10 to the negative sixth for that. So to solve for x, I square rooted that, and I got 0.001, which is also 1 times 10 to the negative third. Yeah. So I got 0.001 molar for x. And then in order to solve for percent ionization, I did 0.001 over 0.1, and then multiply by 100. So I did 0.001 divided by 0.1, I got 0.01, and then I multiply that by 100, and I got 1% ionization again. Did you get it again when you did the calculation, Lone?
Yes, thank you.
Awesome. Okay, are there any other questions about that one? Okay, then for this next one, we have to determine the pH of a solution that is 1.55% NaOH by mass, and you have the density again. So this is like basically the exact same thing that we did for, where is it? Here it is. Determine the pH of a solution. This is basically the exact same thing that we did for this one, except we have a strong base instead of a strong acid here. So it'll be kind of different when we have to figure out pH, because we'll end up getting our concentration of OH minus instead of our pH. So for this one, we have like how we did last time. Do you remember how we did like the 1.09 over 100? We're gonna do the exact same thing, except now we have 1.55% NaOH by mass. So we're just gonna assume 1.55 grams of NaOH per 100 grams of solution, just to keep that ratio and that percentage the same. And so we were also given the density of the solution as 1.01 grams per milliliter. So if we multiply the grams of solution by 1.01 over 1 milliliter, then we'll end up canceling out our grams of our solution, and then we can convert to liters in order to get it into like standard form for molarity. And then finally, we can use the molar mass of NaOH in order to get our moles of NaOH. So we end up actually having moles of NaOH over liters of solution. And when we do that, I got 0.391 molar NaOH. And so because this is a strong base, that means that it dissociates completely, which means it dissociates completely into Na plus and OH minus. And so in this case, we'd have, that's weird. You'd have OH minus equals 0.391 molar, And so your POH would equal negative log of this OH minus concentration. And then once you did the negative log of that, you would get 0.407. That's your POH, not your pH, and the question asks for your pH. So to solve for your pH, you just have to do 14 minus POH because because POH plus pH equals 14. And so when you do 14 minus 0.407, your pH is actually 13.59. And this should make sense to you because, and since NaOH is a strong base, your solution should be really basic, right? It should be really basic or really like a much above 7 and much closer to 14. And if you had put 0.407 as the answer, that would mean it was a really acidic solution, which maybe wouldn't have made sense. And so when you have the pH as 13.59, that makes more sense for a strong base that's added in a solution. I think that any of the ones that I saw that had mistakes in this one had put the 0.41 as the answer instead, and you just must have forgotten to convert from pH to POH, or sorry, from POH to pH. Are there any questions about that one at all?
Yeah, that was me.
Yeah, I did that. I don't think it was just you. I think that lots of people did them.
All right.
It's like so hard to, keep track of everything. So because everything has like such similar names. Okay, are there any other questions about that one?
I have a question. So does the density really matter for this, or could you have just done it hold on.
The density, I guess like in this case, it doesn't matter like so much. It wouldn't make like a huge difference for your calculation because your density is so close to 1 anyway that it's almost like you've been multiplying by 1. But if your density was like 5, for example, it would make a really big difference because you have to cancel out your grams of your solution and get it into like grams per milliliter. Does that make sense?
Yeah.
You want it in milliliters. Just, I guess in this case, it doesn't make a huge difference because it's so close to 1 anyway. That with sig figs, it doesn't make a huge difference.
Okay, thank you.
Mm-hmm. Okay. Are there any other questions? That's a good question. Okay, so for the next one we have determine the POH. So now we're kind of doing the opposite, where we don't have to solve for pH, we just are trying to find the POH of a solution that is 0.125 molar CO3 2 minus, and it gives you the KB of CO3 2 minus, which is carbonate, and it's 1.8 times 10 to the negative 4th. So we have like kind of the opposite for if you remember, like for your weak acid, you have Ka equals H3O plus times your conjugate acid over your weak, H3O plus times your conjugate base over your weak acid. Whereas for your base, you have OH minus times your weak acid, which is your conjugate acid, over your weak base. And so if you looked at this in terms of like actually figuring out for CO3 2 minus, you'd have H2O, which is it's a liquid, so it would be liters, so it wouldn't be in your equilibrium expression, plus CO3 2 minus, and it is aqueous, so it would be included. You have HCO3, so you have I think this is called bicarbonate, HCO3 minus aqueous plus, because you would have just taken a proton from water, you'd have plus OH minus aqueous. And so when you actually wrote your equilibrium expression, you would have OH minus times HA, which is your conjugate acid. In this case, it would be HCO3 minus over your weak base, which in this case is CO3 2 minus. And so in order to solve for the OH minus and the POH, did I ask for this? I guess I just said POH, but you'll have to determine OH concentration in order to figure that out anyway. In order to do this, then you'd have to have this equation set up where you have KB equals OH minus over HA over A minus. And so you would kind of do the same thing where we're going to assume a small x approximation, and then we'll go back and check to make sure that that approximation is valid. So because in an ice table, when we did our change here, you'd have your concentration of, in this case, it would be 0.125 molar. And then this, these would both be 0 in the beginning here. And then when you had the change, you would add X to both of them because you'd have the CO3 2 minus turning into both of these. And so you would subtract it from there because that's reacting. And then you'd end up having a concentration of 0.125 minus X for carbonate, and then X for HCO3 minus, and X for OH minus. So when we do the small X approximation, we're just saying that this number is so small that it's basically just going to be 0.125 by the time we subtract, because with sig figs, it's negligible difference. And so that's what we plug into our equation here. I'm going to erase this. So we plug into our, oops, that's what we plug into our equation here. When we have, okay, so we plug into our equation here when we have x squared over 0.125. The 0.125 is the initial concentration of carbonate. The x squared is the concentration of HCO3 times the concentration of hydroxide. And then our Kb, we were told it's 1.8 times 10 to the -4. That's what we have here. So in order to solve for x, we would take 1.8 times 10 to the -4 and multiply it by 0.125. And then we would square root both sides, and our x would be equal to 0.0047 molar. So now, before we go any further, we have to check to make sure that our small x approximation was, that it was valid, that it was okay. So we do our concentration of OH, that 0.0047 molar, over the initial concentration of our base, which was 0.125 molar. We multiply by 100%, and we get 3.8% dissociation, which is less than 5%. So it's okay that we use the small x approximation. So in order to solve for POH now, we already have our concentration of OH minus. So we have to do negative log of OH minus to get POH. And so you would do POH equals negative log of 0.0047, and you would get a POH of 2.32 as the POH for the solution. Are there any questions about that? Okay. So for this question, we had to determine whether each ion is acidic, basic, or neutral. And so you can kind of talk this through. Okay, so for HI, what is like the either the conjugate acid or the conjugate base of HI? Or sorry, I just literally said it. It's HI because it's I. The conjugate acid of it is going to be HI. Is HI a strong or a weak acid?
Strong.
Strong.
Exactly, it's a strong acid. So if it's a strong acid, will that make its ion weak? Or sorry, will it make it acidic, neutral, or basic?
Neutral?
Yeah, exactly. It'll be neutral. And I hope that that makes sense because it didn't always make sense to me when I was in chem. But the idea is that, like, when you have a strong acid, it's dissociated so much that, and like it just stays dissociated in the solution. It just stays H plus and it stays I minus in the solution. The I minus, because I is so electronegative and there's just one negative charge on it, it's so stable, it's able to hold the negative charge on it so well. It really doesn't need like a hydrogen on there. And so it's not trying so hard to bond with an H It's not trying so hard to accept a proton. And so because of that, it makes like a super, 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 super weak base. Like HI is such a super strong acid that I minus is such a super weak base, conjugate base. And because it's like so weak, it doesn't even try to bond with a proton. And because of that, the I minus is actually neutral. Are there any questions about that one so far? Okay, and the same idea kind of holds for, just gonna skip for a sec and go to C. The same idea kind of holds for C here, where Na plus, if you have NaOH, NaOH is such a super strong base that when it dissociates, it completely dissociates, and that Na plus is so happy to have lost an electron. It's so stable, just getting to be a cation, that it doesn't need to bond to any hydroxide. And so it's so happy to be just to be by itself. That's also like such a super weak conjugate acid that it's actually neutral. And so because of this, both I and Na are weak. Or sorry, not weak. They're neutral. I keep calling them weak because I was thinking of them as super weak conjugates, but they're actually neutral. Okay, let me clear that. And then for the others here, the next one I think is easiest to think about because I think this C7H5O2 is the most difficult one to think about. So I'm going to start off with the F minus here. The F minus is the conjugate base of HF, right? And HF is a weak acid. And so the F, it wants to be able to, it's like, because it's a weak acid, it doesn't really want to dissociate from the H that much. It's not that stable holding the negative charge by itself because H is just, or because F is just small atom, even though it's really electronegative. And so because of that, the F minus is actually basic because the conjugate of it is an acid. So F by itself is a conjugate base. It's like adding in, if you added in a conjugate base, something, it would make a basic solution. F minus is a conjugate base, so it ends up making a basic solution. Kind of on the flip side here, NH4 plus is, it's a really weak conjugate acid, right? Because you have, you'd have NH3 that would get added to water. And it would end up making NH4 plus OH minus. So NH4 is actually the conjugate acid here. It's an acid. And so if it's a conjugate acid, even though it's a weak conjugate acid, it still is a conjugate acid. And so because of that, it's going to create an acidic solution if it's added to a solution. And so NH4 would be acidic. So I think the last one to talk about is going to be the most difficult one because it has some, even though they're bonded to a carbon or to carbons, still has some H's in there. Maybe kind of confusing to think about what this is. But because it has a minus there, it's usually it is the conjugate acid of HC7H5O2. And then because it's the conjugate base of this weak acid, it would make the solution basic if it was added to the solution. Because if these dissociated, then you'd have just C7H5O2 minus, and it would want to bond to a proton because it wouldn't want to hold on to that negative charge. So it would want to find a proton. It would be weakly basic. It would be a proton acceptor. And because also those protons are bonded to carbons, and so it's not going to be those hydrogens would never be used to donate to to be proton donors like an acid. Does that make sense? Are there any questions about that one? Do you want to talk about any of them further or anything like that? Or does that make sense?
Can you
That
just
makes sense.
the C7H5O2 again?
Yeah. So each of these, to think about it as like in terms of like what it is like the conjugate of. And so because C7H5O2 is the conjugate, so first there's a minus, which is the first hint. The other hint is that it's bonded to these H's. If it's ever written like C to the like so C with a subscript or something, H with a subscript or something, and O with a subscript or something, that's not going to dissociate into something further. It would usually have like an H plus in front that was going to dissociate. So those H's are not acidic protons. They're just H's that are bonded to carbons. And so for C7H5O2, the conjugate of it is HC7H5O2. And so this is a weak acid. And when it dissociates into H3O plus and C7H5O2 minus. And because it has this minus sign here, it's holding on to that negative charge. It really wants a proton so that it can be stable. And it doesn't have that negative charge anymore. So it actually wants to be, it's a proton acceptor. It wants to receive a proton, and because it's a proton acceptor and a conjugate base, it's actually a base. So the solution will become basic once you added it in. Does that make sense?
Yeah, thank you.
Are there any other questions about this? I think maybe it's not so hard for you guys. I don't know. When I first learned this, I thought this was like the hardest concept to figure out. I don't know why it was so tough, but are there any other questions about this? Okay. If not, then we'll have a really similar like prompt for this next one that has it has salts instead of just one ion. So you have to figure out which of these ions is the important one to consider. So you have to figure out which, determine whether each salt is going to form a solution that's acidic, basic, or neutral. And so for FeCl3, okay, so FeCl3 would dissolve into Fe 3 plus and 3Cl minus. And so what is the conjugate base of Fe 3 plus? What would it be? Fe what? It would be FeOH3. And so FeOH3, do you guys remember if it's a strong acid, or sorry, a strong base, or if it's a weak base?
Would it be weak?
Yeah, it's weak because if you look back to your solubility rules, iron's one of those things that once it bonds with, like iron is not super soluble. So when it bonds with OH with hydroxide, it's still insoluble, which still makes it a weak base. And then so actually I'm gonna put that down. So this is weak. And then we have to consider Cl. What would be the conjugate acid of Cl minus?
HCl?
Yeah, it would be HCl. And HCl is a strong acid, right? So of the two of these, which ion is it going to be, the Fe3 plus or the Cl minus, that ends up determining if the solution is acidic or basic? Would it be the Fe or the Cl that determined if it was acidic or basic of the solution once the salt is dissolved in it? Do you have any thoughts?
Yeah.
Well, Cl is so strong, or the HCl is such a strong acid that once the Cl minus is dissolved in there, it's completely dissolved and it's not trying to bond back to any H's. It makes it like a super, 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 super weak base. And because of that, when you have a solution that has like a strong acid dissolved in it, or sorry, you have like the conjugate acid of, or the conjugate base of a strong acid dissolved in there, like Cl minus, I minus, it ends up actually being neutral. And so the Fe is the weak one, which actually ends up the FeOH3, because it's a weak acid, or sorry, a weak base, it actually ends up being the stronger conjugate acid. And because of that, the solution is acidic, because that Fe3 plus is more acidic than that Cl minus is basic, since it's part of a strong acid. Does that make sense?
Yes.
Okay. So it's kind of the same concept for these ones. So now we have like NaF, for example. You have your Na and you have your F. So the conjugate base of Na would be NaOH. Is that a strong or a weak base?
A strong base?
It's a strong base. So will Na plus, will it be a really strong conjugate acid, or will it be a really like a super duper weak, or sorry, yeah, will it be a super weak conjugate acid or a super strong conjugate acid?
Weak.
Exactly, yeah, like
Yeah.
it does not matter. Like it's so dissociated from OH minus, it's totally stable by itself. It does not need to bond to a hydroxide. So it's a super weak acid. But HF on the other hand, right? Is HF a stronger or weak acid?
Weak.
Exactly. And so is F gonna be, sorry, is F minus gonna be a stronger or a weaker conjugate base?
Stronger.
Right. So because of that, the solution is basic. So it really comes down to like, when you look at these ions here, which one of these comes from a strong acid or base, which one comes from a weak acid or base? A weak acid or base is going to end up having a really strong conjugate, because it really needs to bond to either the hydroxide or that proton in order to be stable. And so if they're both weak, you have to figure out like concentration. So if I just said like, if I had given you like FeCO3, you wouldn't know whether it would be acidic or basic, because it would depend on the concentration of stuff, because these are both weak. But in another case where I give you like RBI, RBI is RBOH, because Rb is an alkali earth metal. This is a strong base, and Hi is a strong acid, which means that they're both going to dissociate 100%, and they're going to be totally fine to exist without having to gain a hydroxide or gain a proton. And so because of that, RBI is completely neutral, because they're both part of strong, their conjugates are both strong bases and a strong acid. But for K2CO3, only the K comes from a strong base. The K comes from KOH, which is a strong base, but CO3 minus or H2CO3 is a weak acid. And so because of that, CO3 2 minus is going to be a pretty strong conjugate base, relatively strong, especially in comparison to the potassium, which makes the solution basic. And then finally for NH4Br, Br is part of a strong acid, is part of HBr, and so Br is not going to be, so Br minus is not going to be strong at all because it's totally fine holding on to that negative charge. It's just like a super, 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 super weak conjugate base. But NH4, on the other hand, NH4 plus, kind of wants to get rid of that proton. It wants to donate that proton. And so it is a weak, it's like a weak acid. And so because of that, the solution is acidic. Are there any questions about any of these? And this is kind of a difficult concept. Any questions at all though? Okay. Then we can go into this next one if not. Okay. So we have to figure out if each of these is weak or strong. And so for A here, well, I guess first, we talked about this before for like strong acids, right? And weaker acids, but the concept is the same for bases. So a weak base is going to dissociate completely, but a strong base is going to dissociate completely. But a weak base is going to not dissociate 100%. You're going to have some of the base still present and some of the acid present as well. Some of the conjugate acid present as well. And so, for example, for NH3 plus here, you'd have NH3 plus acting as a proton acceptor. And so you have some of your base still present, some of your conjugate acid present, and some of your OH present. Because of this one, A is weak because it's not dissociated 100%, you can still see some of this base being present in here as NH3. For OH minus and for NaOH, it is a strong base because it's dissociated completely. You can see that in this, you don't see any where the Na is bonded to the OH here. The OH is this like red because you have the O is the red and the white is the H. You don't see that the purple Na being bonded to any of those red and white OHs. So it's a strong because it's completely dissociated. And then same down here for D for strontium OH minus. You have all of the strontiums, these green ions are completely dissociated from the OH minuses. And so because it's completely dissociated, it is strong. But on the other hand, for this one here, you have HCO3 minus present, and you also have H2CO3 minus, or sorry, you also have H2CO3 present. So this base hasn't completely dissociated, and you see both the base and the conjugate acid present. So it is weak. Oh my gosh. Okay. Are there any questions about that one? Okay. So this next question was, in which of these solutions does NaNO2 and where'd it go? They're not included in here. Okay, so I'm just going to talk it through just because I think it's a good one to go over, but I don't think that I actually included it on the exam when I was copying my questions in. But the question was, in which of these solutions does HNO2 ionize less than it does in pure water? I thought this question was interesting because it kind of like refers back to the ionization of like how the dissociation of a weak acid here. And so the thing to consider here is that in water, you would have NO2 would dissociate not completely, but it would dissociate according to its Ka value. But if you had, and it would dissociate according to this equation, it would dissociate according to H2O plus HNO2, and it would be aqueous. And it would end up, because it's an acid, it would be H3O plus aqueous and NO2 minus. And so for this one, the answer is D, because according to like Le Chatelier's principle, if you were to have NO2 in the solution already, because NaNO2 would dissociate into Na plus and NO2 minus, you'd already have one of the products, which would push it back into this direction towards the reactants, and it would end up causing HNO2 to not proceed in the forward direction as much as it would in like H2O, whereas all of the rest of these like wouldn't have any impact on the dissociation of HNO2. So sorry, I did not include that one in the exam. I must have just missed it when I was like, you to copy and paste all the questions into Canvas. So I must have just missed that one when I was copying and pasting, but I'll include it in the answer key still if you wanted to take a look at that one if you had any questions. Especially the ones that were actually on the exam. For this one, you have calculate the pH of a solution that is 0.195 molar in HC2, H3O2, and 0.125 molar in K2, KC2, H3O2. And you have the Ka value of HC2, H3O2. So for this one, you remember the Henderson-Hasselbalch equation? It is the pKa. So this is all about buffers now. I guess actually is important to go over first. So if you remember buffers, do you guys remember what the point of a buffer is? And that you guys probably just learned it before you went on to break it. It's probably been like a week since you took a look at it. But does anyone remember what a buffer is?
I forgot what a buffer was, to be quite honest.
No, it's fine. It's been so long. And I know that you guys just went over it, I think, right before spring break. So it's easy to forget. Does anyone else remember what it is, or just want to go over it?
Yes, please.
So just go over it then. So the whole point of a buffer is basically that if you add a weak acid or a weak base and its conjugate, either acid or base, it can kind of like prevent, let me go to this because I have more space to write. It can kind of prevent the pH from changing too much. And so for example here, you'd have HC2, H3O2. And if it we're in water then, plus H2O, you get H3O plus C2, H3O2 minus. So the whole point of buffers is that you already, when you're dissolving in the KC2, H3O2, because it's a salt, because K is going to make this, the potassium is going to make this soluble, you end up getting, when you dissolve this, you end up getting K plus and C2, H3O2 minus. So you end up already producing one of your, or you already end up producing your conjugate base. You already produce your C2H3O2 minus that your HC2H3O2 would have dissociated into. And so the idea here is that if you dump in, a strong acid here, so if you dump in HCl, instead of just completely changing the entire pH, you end up forming, you'd have the HCl react with the C2H3O2 minus to form HC2H3O2, which would then go back into this equilibrium expression. Oops, that was a really big swipe. Which would then go back into this equilibrium expression here. So you'd have something that would prevent it from just having like HCl take a huge hit on your system, because the C2H3O2 minus is going to react with HCl, and it's going to form HC2H3O2, which would go back into this equilibrium expression and kind of hit, kind of go back to make sure that the pH doesn't change too much. On the flip side, you also have this conjugate acid here. So if you were to add a weak base like NaOH to this buffer, you would end up adding NaOH to HC2H3O2, which would then end up making, this would dissolve into OH minus, and then you'd end up having H2O plus C2H3 O2 minus, which was again your conjugate acid up here, which would then cause this thing to go back into the equilibrium, into this equilibrium expression again and hit equilibrium. So it really prevents the pH of the reaction from changing too much, even when you're adding in a really strong even when you're adding in a really strong acid or a really strong base. So it kind of just keeps the pH the same. You might be like, what does this even matter for? Like our blood is a buffer, for example. So like that way, if something, you have like an acid inside your body, you end up having like your pH doesn't just like change in your blood super rapidly and you don't like die because your pH just got super basic or super acidic, or like water is a buffer, was a really good buffer as well. You have like these buffer solutions in water with different salts and stuff in there. So for example, the ocean you don't just have like acid rain get into the ocean doesn't just get like super acidic and kill all of the fish. So buffers are really important in nature, and then also like I'm not too familiar in medicine and stuff, but I think they're also really important for medicine and whatnot to make sure that nothing's getting too basic or too acidic. So are there any questions about like the theory of a buffer first?
No.
Okay, does that make sense? Is that helpful? Does that jog your memory a little bit?
Yeah, a little bit, yeah.
Okay. Does anyone else have any questions on it? I know they're kind of like a weird topic. The whole point of them basically is just to remember is that you want to have something, either the conjugate base that can react with a strong acid, or you want to have the weak acid react with a strong base to form the conjugate. You have a weak acid react with a strong base to create the conjugate base. No matter what, you're creating something that's in this equation to keep equilibrium, or which will cause it to keep equilibrium and make sure that the pH isn't going to change too much. But there's one equation in particular that's really useful for buffers, which is pH equals pKa plus log and I want to double check this, but I'm pretty sure this is what it is. I'm pretty sure it's your base, your conjugate base over your conjugate acid, or over your weak acid. It's called the Henderson-Hasselbalch equation. And so does anyone remember what a pKa is?
Isn't it like the log of Ka or something like that?
Yeah, exactly what it is. It's
Uh.
negative log of Ka. So like how pH is your negative log of your H concentration, or POH is your negative log of your OH concentration. pKa is just a negative log of your Ka. And so that's how you solve for the pH of a buffer. And so let me clear. So you can use that Henderson-Hasselbalch equation to solve for the pH of this equation, because you're given the Ka, you're given the concentration of your weak acid, and then you're given the concentration of this KC2H3O2, which ends up dissolving into your C2H3O2 minus, which is your weak acid, or sorry, your weak base here, your conjugate weak base. And so you just plug this into the equation here. So just like Bryce had said, your pKa is your negative log of your Ka value. Your Ka is 1.8 times 10 to the negative fifth. Then you have to do log of your conjugate base, your C2H3O2 minus, in this case 0.125, over your weak acid, which in this case is 0.195 molar. And then you just do the calculation. I think it's one of the simpler like equations that you have to use, just to make sure that once you make sure that the setup is correct and you have all the numbers in the right place, it's not too not too strenuous calculation like some of the other ones for like when we were doing like integrated rate laws and kinetics and stuff. So it's not it can be kind of overwhelming, but I don't think that it's too, you guys can definitely handle it in comparison to some of the math that you've done so far this semester. And so you end up getting negative log of 1.8 times 10 to the negative fifth is 4.7, and log of 1.25, or sorry, of 0.125 over 0.195 is negative 0.193, and your final pH is 4.5. Are there any questions at all about this? Okay. If not, then we can go to the next question, which is a really similar question. This one just gives you a different Ka value and a different solution here. So just like last time, you can use the Henderson-Hasselbalch equation, and you just do your negative log of 2.9 times 10 to the negative 8th, which is your Ka value, over, plus log of 0.155, which is your A minus, your conjugate base, because KClO is going to dissolve into K plus and ClO minus, and ClO minus is the conjugate base of HClO. And you would then have your you have to put it over top of the concentration of your weak acid, which is the 0.135 molar in this case. So you get 7.5 plus 0.06, which gives you a final pH of 7.6. Are there any questions about that one? Okay. Then we can go forward here to this next one. A 250 milliliter buffer solution is 0.25 molar in acetic acid and 0.25 molar in sodium acetate. Acetic acid has a Ka value of 1.8 times 10 to the negative fifth. So the first question is, what is the initial constant or the initial pH of this solution, and then what is the pH after the addition of 0.0050 moles. And I think that when I actually asked this in the quiz, I only said what is the pH after the addition, but I think you have to solve for it anyway. So if you wanted to solve for the initial pH, it would end up being pH equals pKa plus log of your conjugate base over your weak acid. So you can just plug and chug, just like here is your weak acid, and your sodium acetate is going to dissolve into sodium plus and acetate, which acetate will be your conjugate base. So you'd plug it all in, because when you do log of 1, you get 0, and 0.25 over 0.25 is going to go to 1. It ends up just being pH equals pKa, which is 4.7. When you search, or when you try to find for the pH after the addition of 0.0050 moles of HCl, you'll have to use an ice table. So the first thing is that because you're adding moles of HCl in, you need to convert everything to moles in order to actually do the equation, or like the actual calculation to subtract. And so you can find your moles of your acetate. So acetate is C2H3O2, and you're told that you have 0.25 molar sodium acetate. So 0.25 molar sodium acetate times 250 milliliters, you're given your volume. Because molar is in moles over liters, when you multiply by liters, you get just moles. You have to convert from milliliters to liters, and then you just multiply, and you get 0.0625 moles acetate. You have the exact same concentration of acetic acid, and of your volume is the same, because you're told that 250 milliliter of buffer solution, and you're told it's 0.25 molar in acetic acid. So you can do that concentration, or you can do that calculation to figure out the moles of acetic acid, and then you plug into an ice table. So if we break this down, because we are adding HCl, HCl is going to just dissolve into, because it's a strong acid. Basically, we don't really care about the Cl, because the Cl is like, we talked about it before. It's not really going to be, it's not going to act as a base because it's going to dissolve completely. So it's just going to become H3O plus and Cl minus. We don't really care about that Cl minus. We care about that H3O plus, because that's what's going to actually react here. And so the H3O plus is what we care about with HCl. And so we have 0.00625, and we have 0.5 moles of our acid here, of the H3O plus. But the H3O plus is going to react with C2H3O2 minus, and it's going to form more of the conjugate acid, the weak acid. And so we have to subtract 0.050 moles, because 0.0050 moles of the C2H3O2 is being converted into this. So we're decreasing this concentration and increasing this concentration, because we're using this and converting it to this. And so once you subtract the concentration of your H3O plus, you get 0.0575 moles of acetate. And you would end up adding it, because you're converting the acetate to acetic acid, because you're combining it with a proton, and then you're converting it into acetic acid. And so you'd end up adding 0.005 moles, and you get 0.0675 moles of HC2H3O2. So now we don't really know what our total volume is here, because we're just told that we're adding moles of HCl, but we didn't tell us like how many, like what the volume of that HCl was. But the good thing about the Henderson-Hasselbalch equation is that you end up having a ratio. So even if these were both over a certain liter volume here, they could both be over 10 liters or 1 liter or 7 liters or whatever. It ends up getting canceled out, because whatever you have it over for the acid, whatever you have the acetate's volume as, it's also the acetic acid's volume. And so these volumes end up canceling out anyway. So you can just put the number of moles in there. And so you would do negative log of 1.8 times 10 to the negative fifth, which is the Ka that was given to you initially, plus log of 0.0575 moles over 0.0675 moles. And you would get 4.74 minus 0.07, which is 4.68. And it ends up actually being 4.7 again with sig figs anyway. So it did, as you can see, the buffer works really well, where it hardly even changes the pH, even though you're adding in a strong acid. Are there any questions about that one? And that's a lot at once. Any questions at all? Okay, so we can go on. We have like 2 more left. To determine whether the mixing of each pair of solutions results in a buffer. And so something I didn't really talk about when I talked about buffers is that I had said that a buffer has to exist between a weak acid and its conjugate base, or a weak base and its conjugate acid, but we didn't really talk about like why it had to be a weak acid or a weak base. And so the idea of that is that the way we had talked about, for example, if you had sorry, I forget what the first one is here. You had HCl, for example, here, trying to act as a buffer. You'd have HCl plus H2O would yield H3O plus Cl minus, which is great so far. But then let's say that we add in, more acid that we want it to react with. So let's say we add in H3O plus. So remember how before when we had added when we had acetic acid and we added Cl in, it didn't really matter too much because you had them both, you had the conjugate base working as a base that would then convert it back into the acid. But when you add acid to Cl minus, we talked about this before, how Cl minus is totally good just being Cl minus, doesn't need that acid added back onto it, and HCl completely dissociates 100%. So if you try to get Cl minus and H3O plus, it's not going to form HCl. It's literally just going to form, it's not going to form HCl. It's literally just going to form H3O plus and Cl minus again. And so when you have that, you can't use a strong acid or a strong base, because since the conjugate ends up being such a weak conjugate base or acid, it doesn't even try to react. It completely dissociates anyway. It doesn't even try to react with whatever you add in. It doesn't act as a buffer because it's not going to do anything when you try to add in a substance. It won't buffer at all. And so a buffer has to be made out of a weak acid and its conjugate base, or a weak base and its conjugate acid. And so in this situation, you have A would work because HF is a weak acid, and NaF is its conjugate, includes F minus, which would be its conjugate base. And D would also work because you'd have CH3NH2 and its conjugate base, CH3NH, or sorry, you have CH3NH2, and then its conjugate acid would be CH3NH3Cl, because CH3NH3 would dissociate from Cl, and you'd have this conjugate acid. So only A and D would work because Cl is a conjugate or is a strong acid, KOH is a strong base, and HCl is a strong acid again, so it wouldn't work. Are there any questions about this one, about 22? Okay. And the last question was, can a buffer be created out of HF and CH3NH3Cl? Why or not? So you might think well, we had just talked about how we needed it to be weak because you need the conjugate to still want to bond to a proton or lose a proton. But if you created a solution with these two, if you tried to create if you tried to create a buffer out of HF and CH3NH3Cl, you'd end up just forming a salt where you'd have CH3NH3 and Cl would dissolve, and then HF would dissolve, but then you'd end up having CH3NH3 bonding to F, and it would end up creating an actual salt. So it would end up not actually creating a buffer, which is why you need to have it be a conjugate. You need to have an acid and its conjugate base, or a weak acid and a weak base and its conjugate acid, because otherwise the anion and the cation, if you had two weaks added together, they're just going to create a salt together and they won't actually create a buffer. Okay, so that was all of the questions in the exam. Are there any questions about anything on the exam or otherwise that you want to go over more? let me just I'm gonna take a screenshot of the attendance. So if you hear a screenshot noise, it's just me taking a screenshot of the participants. Did I go over anything? You're welcome to go if you're feeling good about anything, or you can hang back and ask questions if you're feeling like you want to go over anything anymore. I know that we've been on spring break, so you might be a little bit out of practice of doing chem, but we'll have another mock exam next week, which is good because I'm pretty sure your next exam is supposed to be on, I think it's on
Next Monday.
Yeah, I think it's on the 29th.
Yeah.
Yeah.
Sadly.
Yeah. So we'll do the mock exam next week, and we'll have another review session from 2 to 4. So feel free to bring questions then too if you have any questions about that we didn't get to go over today.
All right. Thank you.
Yeah, of course. Have a good rest of your night, and I hope that this week back at school is good.
All right. You too. Bye.
Bye.
I have a quick question, but it's based on a topic that we have, like it was exam 2 material.
Oh yeah.
So for one of the questions, we had to identify the rate law based on graphs, and some of them were curved. And I was wondering, how can we identify the rate law based on a curved line?
So the whole point, let's try to see if I can see what that